we're going to kind of go backwards on this. If we sketch the graph of this, and you should recall it, if it's exponential growth, this is my coordinate plane, if it's exponential growth, it goes like this, right? Remember these graphs? If it's exponential decay, it's coming the other way, and it goes like that. Okay, so our domain, I'll throw these in, how about some green? Domain's what for exponential growth and exponential decay? What x values? All real numbers, yeah, all real numbers. Okay, how about the range? You should write this. Range is all real numbers greater than 0. That's a greater than symbol. Not my best, but a greater than 0 symbol. Remember, there's an asymptote. The the x-axis is an asymptote. Okay, the y-axis is an asymptote. It never crosses over. I'm sorry, I keep misspeaking. The x-axis never crosses over the x-axis. Okay, so I'm going to jump down to asymptote. The asymptote is y equals 0. That's your asymptote. Never ever going to cross over that when you're an exponential function. Okay, and what point is on all exponential graphs? This point right here.
0, 1.
Over 0, up 1, absolutely. Whether you're decay or growth, you have the point 0, 1. Okay? So, the question is, and I'm going to stop recording for a minute, it says, what happens when you need to solve for x? Tricky. But things to know. It's the inverse of an exponential function. So their graphs are reflections over the line y equals x. Logarithms are used to find the exponent, like I just said. When the exponent is an x, and you need to solve for x, you use a logarithm. You can switch between exponential and logarithmics with the circle method, which I'll show you here in a second. In common logarithms, if the base is not written, it's understood that the base is 10. Okay? So, you should recall from last year, and if you don't, it's no big deal because you're going to see it right now. If you want to turn a logarithmic function into an exponential function, you do the circle method. Start with the base and say b to the y equals x. Okay? So this is equivalent b to the x, I'm sorry, b to the y. B to the y equals x. Okay? That's the circle method. Start with the base, circle up, b to that power equals x. Alright? If you start with a logarithmic, if you start with an exponential, this is the base of your log is the base of your exponent, and then just switch the other two. The domain for an exponential is what the range was for an exponential. So the range, or I'm sorry, the domain is all real numbers greater than 0. Okay? The range for a logarithmic is what the domain was for an exponential. So the range is now all real numbers. Alright? If the point 0, 1 it was on every exponential graph, then what point is on every logarithmic graph? 1, 0. Okay? If the asymptote y equals 0 was on every exponential graph, then what asymptote is on every logarithmic graph? X equals 0. Everything was the opposite. And if our exponential graph, I'm going to put it on here, if our exponential graph for exponential growth looked like this, then our logarithmic graph is going to be just the opposite of that. Okay, so we're going to have, now our asymptote, instead of being the x-axis, is now the y-axis. It's going to look something like this. Okay? Or you could be coming across this way and look like this. But if you look at either one of those logarithmic graphs, the domain is all real numbers. Now it's not going to cross over the x-axis or the y-axis. The range is going to be all real numbers. Okay? It's going to go up and down forever. The point on all exponential graphs is now 1, 0. asymptote at x equals 0, aka the y-axis. So it's the exact opposite, the exact flipped of the exponential graph.